but a circuit basically also getting us into a control theory problem. So I want to look at the second order structure, 2 op amps. The first structure, actually a very standard 2 resistors, the same one in feedback, so I expect a gain of -1 and a time constant for C. And in fact, this is the kind of core equation I would expect for that kind of an element. I would also get a second one, and here I'm actually talking about it in terms of conductance, G and G, and then if I put that together, I get this equation, which is a little more complicated. And then I just sort of say, let me normalize this by a basic time constant, RC or C over G. You definitely want to normalize. Normalizing is huge. It makes a huge difference for almost everything else you're going to put together. Now you might look at these things and go, wait, this feels a lot like that second order section that Carver-Mead came up with, but now in op-amp form. And that's exactly what this is. And so not shocking in terms of those dynamics. So what I'm going to do though with the time constant, I'm going to normalize time. I'm also then going to take the minus of E1, because again, these are inverting op-amp configurations, so I think the math gets a little bit easier if I get a minus sign in there. So I can work with this one. I'm also going to then talk about the input really is going to be U of t. That's going to be coming up from this point right here, which is that coming off of that basic R, so we expect a simple structure there. So if I take this structure, I put the extra, invert the V into this, I put the time constant into it, I'm going to get this state equation. And this is really cool because now I got a state equation, one variable parameter A. Notice this A is a negative resistance. You can get negative resistances. And I'm just kind of using it as a spot here. This one is going to be one that's going to shift between positive and negative resistances. And so when I use this, this gives me a very nice structure to begin with in terms of this second order structure. And again, I get my Y. So this is my C, this is my B matrix, which is useful because once I have a B and C matrix, I can ask different questions. 1 and the A matrix. So for 2 cases, let's say for the A is equal to 1 case, I would get this matrix with a 0, -1, -1, and 1. This gives me stable eigenvalues. Certainly they have an imaginary part to it, so I would see some sort of ringing on the step response. If I take A equal to 3, well now I get 2 -3, 1, -1. This gives me an unstable situation. And so this gets to be the fun one in terms of a control system to say, well, could I build a controller around this? And so sure, I could start off with here's a controllability matrix and the observability. Do I have the capability? Yes, the eigenvalues are all pretty bounded. It works pretty well. Cool. So then what am I going to do? I'm going to want to do an LQR to do this optimal control, part of which is then, let me just assume the cost is equal and there's no cross terms. So Q is an identity matrix, R is an identity matrix. That kind of simplifies my math a bit here. And then once I get to this point, I go, this is great. I've got my matrices. What am I going to do? Usually I go look at MATLAB and go solve for P, which it can solve this beautiful Riccati equation, and it gives me my control vector. I can do something similar for LQE. We're going to start by assuming that since these are all fixed components, there's no variability. I could have put a variability to say, hey, this is going to be some statistical measure. There's some variability between resistor components and capacitor components. I just didn't do it here. The second part is to say there could be some level of noise. And this would be like noise that's coming off the resistors that I'm measuring at the output voltage. So maybe the total noise measured over the whole bandwidth is like 100 microvolts. That wouldn't be unusual. And so I'm going to call that sigma. Well, what I'm going to need to do then is create something that gives me an estimate of the states. And then I need K sub F, which is then this sort of Kalman value, to say, hey, this is how I can get this to approach the actual solution. Well, we know, again, this is going to be core value based on Qn and Qw. Well, Qw isn't in that. Qn is related to sigma. I get another Riccati equation to which you go, that's exciting, yay. It turns out the solution to this is 4 and 2 for Kf. It turns out your solution for P is proportional to sigma. And this is actually kind of interesting to take a look at in these structures. I also, for fun, kind of looked at the LQR problem and realized that you can actually get a very continuous change with A on both P11 and P12 values in terms of the solutions. Because again, the P11 and P12 values are exactly what fit into case of R. And so this is very useful. I would suggest certainly when you don't know what else to do with these values, go to MATLAB. MATLAB is a really good way to solve this. But certainly this is important to kind of know how to set it up. And then the other thing to notice is that you might worry about what's going to happen to the noise. The P tends to absorb the sigma, and your actual value in the end tends to be still pretty balanced. So in the end, this is one good example of how you can kind of walk your way through a controller structure and then kind of work and kind of see what you get.